Hi, my name is Cation and I'm a final year PhD student in the groups of David Scanlon at University College London and Aaron Walsh at Imperial College London. And our research uses computational modelling techniques to understand and predict the properties of solid-state solar cell materials, looking both at bulk properties as well as more material-specific behaviour such as defects and disorder. Today, from my hotel room here in Boston, I'm going to speak about some of our recent work looking at the impact of cation disorder on the performance of the emerging class of ABZ2 chalcogenide materials, which are promising candidates in the field of low-cost, non-toxic and stable solar cells. Okay, so you might not have heard of these, but there's this new material that some people are talking about, and it's called perovskite. And it's recently emerged as a promising alternative to silicon, being cheap, efficient, solution processable, meaning it can be made or manufactured quite cheaply, as well as being readily tunable thanks to its mixed composition and solution processability. However, they require the presence of lead, which is toxic and unstable in air, and this has hindered its industry application thus far. So given the many advantages of perovskites, but alongside those stability and toxicity concerns, this has led researchers to look at trying to understand the key performance properties of the perovskites to then try and identify alternative materials with similar properties and thus hopefully performance, while avoiding the presence of lead and achieving a good level of operational stability. In particular, the rapid improvement in efficiency of perovskites in such a short time span gives us hope that we can adopt a materials by design approach, learning from their success and identifying these so-called perovskite-inspired materials. So we've looked at a wide range of these materials during my PhD, and in fact, I'll actually be speaking about a different class of perovskite-inspired material in the EN04 symposium, which is the vacancy ordered perovskites. So if that's your sort of thing, please check that out as well. However, the class of perovskite-inspired material I'm going to be focused on in this presentation, which has experienced a dramatic rise in research interest over the last couple of years, is that of the ABZ2 disordered chalcogenide materials, where A and B are cations and Z is a chalcogen anion, such as sulfur or selenium. So they have this rock salt crystal structure, but with a disordered 50-50 occupancy of the cation site by the A and B cations. A key chemical similarity with conventional perovskites is the presence of this MX6 octahedral motif. However, a key difference with the perovskites is the closer packing of the octahedra here. So we no longer have that A-site spacer ion that you have in conventional perovskites and only corner sharing octahedra, now having both corner sharing and edge sharing octahedra. So this close packing and high dimensionality, along with disorder on the cation sublattice, is actually one of the key benefits of this material class over other perovskite-inspired materials, such as the double perovskites or the vacancy ordered perovskites I just mentioned, because we now have a pseudo-direct band gap with a low energy, ideal for solar absorption, as well as low carrier masses. Another beneficial difference with conventional perovskites is the presence of metal chalcogen bonds, which are stronger than metal halide bonds, and so bestow a greater degree of thermodynamic stability to this class. So these materials are synthesized in solution, again, one of the key selling points of perovskites, and typically in the form of nanocrystals, though thin films have also been made. So in our studies on these materials, we sought to understand the impact of disorder on the cation sublattice and on the solar cell performance, and to then try and optimize or to leverage these insights to optimize the photovoltaic performance. So in general, modeling atomic disorder presents a real challenge for theoretical methods, which prefer to deal with high symmetry ground state materials. So here we employed a range of computational approaches to achieve a well-rounded picture of disorder in this material, or these materials, I guess, including the special quasi-random structure approach, in which you generate a supercell of the material, but with the cations arranged quasi-randomly. So this means that the radial correlation functions of the cations match that of an infinite perfectly random arrangement. So this provides us a good approximation of the fully disordered material at a reasonable computational cost, and allows us to estimate the thermodynamic cost or accessibility of disorder in these materials. We also employed a structural enumeration approach to kind of, query the behavior between these two limits of total disorder and total order. So in case there was any cation correlations or clustering behavior. And to do so, we generated all possible symmetry inequivalent cation arrangements within a 32 atom supercell, and then calculated their structural, energetic, and optical properties to correlate this with the photovoltaic performance. So in the first of these studies, we collaborated with the group of Gerasimos Concentrados in ICFO in Barcelona, looking at the silver bismuth sulfide member of this family. And he'll, time permitting, be speaking a little bit about this in the EQ04 symposium, so you can also check that out. So our key finding in this study was that optical absorption was greatly reduced when you get this clustering of cations in the material, and rather we have an absorption coefficient approximately 2 times greater when you have a near random homogeneous cation distribution in the material. So to analyze the interplay between these cation distributions and the electronic properties, I looked at the local electronic density of states as shown here. And you'll see this type of plot again later on in this talk. So on these heat maps, we plot the electronic density of states as a function of both energy on the y-axis and position on the x-axis. And here we show alongside the average cation distribution within the supercell. So what we see here is that for the low band gap clustered configurations, we get a clear separation of our bismuth-derived conduction band minimum, which of course correlates with high bismuth density in the material, and our silver-derived valence band maximum. So this spatial segregation of the upper valence band and lower conduction band results in low orbital overlap and thus a weak optical transition dipole moment and poor optical absorption, as we saw on the previous slide. In the case of homogeneous near random disorder, however, we get a near homogeneous delocalized VBM and CBM as expected, and thus strong optical absorption. So these predictions matched excellently with experiment, which found similar absorption enhancements when applying a low temperature annealing treatment to the as synthesized nanocrystals to induce this entropically driven shift to a more homogeneous cation distribution. In doing so, we actually obtained a material with an absorption coefficient higher than any other currently studied solar cell material, which was really exciting. So I don't have time to go into the details here, but we followed this up with careful targeted measurements to directly compare the theoretical predictions with the experimental results, which gave us confidence in our model of the underlying atomic behavior that was driving these absorption enhancements. So these absorption enhancements resulted in the development of record-breaking solar cells by our collaborators, yielding devices with over 9% efficiency in an ultra-thin architecture, demonstrating the exciting potential that this disorder engineering approach has as a powerful materials design tool. 2 other records held by this material are that it has the highest absorption coefficient of any currently studied photovoltaic material, as I just mentioned, as well as the highest efficiency of any bismuth-based solar material, which are a class of materials that have been heavily investigated over the last decade as lead-free alternatives. So how do you further your understanding of the dominant chemistry within a material class? Well, a tried and tested method is to change something and see what happens. See, does it match your expectations? So with this in mind, we went on to look at the sodium isomorph of this material, where we isovalently substitute silver with sodium. Initially, we find similar promising properties with this extremely strong optical absorption in the low energy range, which is reflected in the high theoretical efficiency for an ultra-thin absorber, as shown here. These ultra-thin solar cells are actually quite a hot topic in the field at the moment, as they have a lot of exciting alternative applications that silicon cannot fulfill. So a lot of these are in terms of non-invasive, flexible solar cells that can be put into clothes, on wearable electronics, and smart devices in your home, so they can just be powered by the lights in your home and not need to be charged or plugged in. Another application area is space, where of course power to weight ratios are extremely important, as well as decentralized power applications in remote locations. However, our calculations consistently showed the presence of these localized electronic states in the band gap of this compound, which we didn't see with the silver isomorph. Looking at the orbital character here and the electron density here, we can see the clear sulfur P nature of these states. And these states in the gap are expected to lead to carrier trapping and recombination, as effectively acting as stepping stones across the electronic band gap for the charge carriers, and thus are severely detrimental to solar cell performance. So why, despite the equal oxidation states of sodium and silver, do we get such different bonding behavior in these two materials? Well, with silver, we have this filled D10 valence subshell, which in this MX6 octahedral motif gives rise to a strong anti-bonding interaction with the anion p states at the valence band maximum, in the same way that we actually have in conventional perovskites, and this feature has often been suggested to contribute to defect tolerance in the perovskites. So this gives us a high energy VBM with strong dispersion. The sodium cation, on the other hand, has an empty noble gas-like valence shell, and so behaves effectively like a spectator ion in these systems with no covalent interaction with the anion p states. This is very similar to cesium or methylammonium in conventional perovskites, for example. So this gives us a low energy non-bonding VBM in the sodium based material, which then allows the emergence of these localized sulfur p states at sodium rich pockets in the material, as the lower charge of the +1 A cation versus the +3 bismuth cation increases the electron energy here. Whereas for the silver-based material, the higher energy VBM effectively screens out these localized states, funny enough, in the same way that this anti-bonding VBM is suggested to contribute to defect tolerance in the halide perovskites. And you can read more about that here in this paper, it's shown below if you're interested. So we can clearly see the emergence of these localized states in the same type of local electronic density of states plot I showed earlier, where we see the formation of a distinct electronic state here that is highly localized in both space and energy. That correlates quite closely with high sodium density as shown by the yellow patch on the upper heat map there. So as expected, these localized states lead to ultra-fast carrier trapping, followed by extremely slow decay and long effective carrier lifetimes, but overall killing solar cell performance in this material. So the main conclusions to take from these works are that disorder presents a powerful tool to tune materials' properties and optimize performance. However, we show that both the nature of this disorder and the cation distributions, as well as the underlying orbital chemistry, are key considerations for the intelligent design of emerging photovoltaic materials. While disorder is often viewed as something to avoid within the materials community, I believe that these results and other recent reports in the field show that that's not necessarily the case, but rather with greater understanding and control, we can tame disorder as a powerful tool for our materials design toolkit, and possibly opening up the possibility to fine-tune performance across a range of applications. So not just solar cells, but thinking also maybe LEDs and thermoelectrics, for example. On this point, I'd just like to quickly plug a talk from a student I've been working with quite a lot in UCL, Adair Nicholson, who'll be speaking about disorder in mixed metal chalcohalides, where again, it provides a useful lever to tune the electronic structure. And funnily enough, the other talk I mentioned in the ENO4 symposium is actually a very similar story of drastically different electronic properties despite equal oxidation states due to differences in frontier orbital character. So if either of those are your thing, please do come check them out. So to finish, I'd like to thank my supervisors, Professors Aaron Walsh and David Scanlon, for their brilliant support and guidance over my PhD, as well as our collaborators in Barcelona, Oxford, Berlin and Cambridge, and of course all members of the Scanlon and Walsh research groups, and you for your attention.